In this problem, this example problem, we're going to look at a horizontal disk, no friction of the axle of the disk, has a mass of 18 kilograms, a radius of 1.7 meters, and we place a 6 kilogram block on top of the disk out near the edge of the disk. The coefficient of friction for the block is 0.4, and then we have a thin massless rope that's wound around the disk, and we create tension on that rope, a constant tension of 7 newtons, and the rope as it unwinds is always perpendicular to the radius line, perpendicular what will become a lever arm as we calculate a torque, but it just comes off there perpendicular to the curve of the disk. We're starting from rest. I want you to calculate with me how much time does this 7 Newton force have to be applied until the block slides off of the disk. So we're in a situation here where we're going to be spinning this disk. As it spins, in order for the block to stay in circular motion, there must be a centripetal force towards the center. That centripetal force is created by friction. However, if friction cannot supply the required centripetal force, the block will go more in a straight line. And not a perfect straight line because friction is still present, but we won't be able to stay on the circle motion, and the block will drop off to the side of the disk. So we're looking down from the top view as we consider this system. Again, 7 newtons created tension here that is constant and always perpendicular to the lever arm. So let's try a few calculations here as to what's happening. Well, one thing that's important for us, the force of friction is creating the centripetal force. How much frictional force is present? How much frictional force is present? So we have, I draw this from the side view, we have 6 kilograms, and that creates 6 kilograms times 9.8 newtons of force. The surface pushes back with that same number. The force of friction itself is calculated with the coefficient of friction times the normal force. So for this problem, when we have a coefficient of friction of 0.4, our normal force is 6 kilograms times 9.8 meters per second squared, acceleration due to gravity. So our frictional force that we have available, you should calculate with your own calculator as well. So multiplying those 3 factors together, I came up with a force of friction of 23.52 newtons. And I'm not actually going to use that, but this force of friction is going to balance the centripetal force required at the critical point when the speed of rotation gets up to a place where friction can't match the required centripetal force. So the way I'm actually going to do the calculation is I'm going to set the force of friction equal to the required centripetal force. So let's do that a little bit over here. So 0.4, 6 kilograms, and 9.8. I'm going to set it equal to, well, what's the mass that's in circular motion? Again, it's 6 kilograms. And we have a v squared. And the radius we're given for this disk, 1.7 meters. So it's a little bit of 6 and 1 1/2 a dozen of another, but instead of calculating this time to get the force of friction, I'm going to cancel that off. If you would prefer to put in 23.52 here for the force of friction, then of course don't drop the 6 kilogram factor. But it saves a little button pushing if we do cancel the 6 and a possible avoid an error. To calculate v squared, I need to multiply these two together and also multiply by 1.7. So just to give you this intermediate number, this v squared I get is 6.664, and take a square root of both sides. So the critical speed here, when the block starts to slip off, 2.581 meters per second. 2.581 meters per second. Well, of course, we're in a rotating system, so it's going to be necessary for us to get the angular speed and then incorporate torque, creating alpha, angular acceleration, and coming up with our time. So that's where we're headed with this. Well, there's a connection between the angular speed and the linear speed. V equals r omega. So we have the linear speed, 2.581, where this block will break free. We know the radius, we're out at the edge of the disk, so 1.7 meters. So we can calculate omega. So let's do that. Omega is going to be this speed we've determined, 2.581. And I'll round off later. I tend to keep extra digits a little bit as I work, so I don't create round off error. Divide by the radius here to come up with omega, and we come up with 1.519 radians per second. So this 7 Newton force is going to create a torque that's going to create angular acceleration that'll bring us up to this angular speed. So let's start working on this. So we're going to need to use torque equals I times alpha. We need alpha because we're going to be working through the equation omega equals omega naught plus alpha t. We're trying to find the time. We're starting from rest, so we know the omega naught is 0. We now know the omega that we want to achieve, 1.519 radians per second. So the missing point here is alpha. That'll be calculated using torque created by the 7 Newton force. The moment of inertia I will give us alpha. So there's a sort of intermediate calculation here of the I value. Let's go ahead and work on that. Our I for a filled-in solid disk is 1/2 mr squared, and 1/2 mr squared would be 1/2 18 kilograms and 1.7 meters squared. You ought to check this calculation if you can see it. 26.01 kilograms meter squared. The torque is force times lever arm. We can use these two numbers because the force is perpendicular to the lever arm here. If I would attempt to sketch in this lever arm, perhaps out like this. But the force is perpendicular to the lever arm, so I don't need to use a cosine theta factor or sine theta factor. Let's just ignore that. Torque equals force times lever arm when this force is perpendicular to the lever arm. So doing that calculation, we have 7 newtons and we have 1.7 meters. That gives us our torque value, and I'm not going to bother to calculate that number. You can, but now I want to plug it in and find alpha. So the 7 newtons and 1.7 meters. The I value is 26.01 kilograms meter squared. And that will be giving us a certain alpha. Now, hopefully you're asking questions along the way here. Is this really the correct I value? This is 1/2 mr squared. Is it the correct I value? Remember, this is before the 6 kilogram object slips off. So in fact, this is only the I for the disk. And we have to adjust this. There's an I for the block. That's just mr squared. If you put in 6 kilograms and 1.7 squared here, the moment of inertia for just the block is 17.34 kilograms meter squared. And we get the total moment of inertia by adding these two together. I almost forgot to do that. I would have had to redone the video. But the total moment of inertia is the moment of inertia of the disk plus the moment of inertia of the block that's in the circular motion. So we add those two together and get alpha. So multiply 7 times 1.7, add these two numbers together and divide, and check the value of alpha. I came up with alpha of 0.2745 radians per second squared. We'll use that alpha now to calculate the time. Since we know the omega, 1.519, and we're starting from rest, let's use this alpha and calculate the time to get up to that speed. So 1.519 radian per second equals 0 for our starting angular speed, plus 0.2745 radian per second squared multiplied by time. So we're going to take 1.519 and divide by 0.2745, and I came up with a time of 5.53 seconds. I'm rounding a little bit now. 5.53 seconds for the time that we have to keep the 7 Newton force constant on the rim of the disk. And when we do that, we'll achieve a omega value of 1.519 radians per second. When we achieve that, the force of friction equals the required centripetal force. As omega gets higher, the speed of the block gets higher and the required centripetal force gets higher, but we don't have any more friction. Friction's limited to that amount for our static friction, and consequently the block starts to slide off. So you might want to replay this, but hopefully you're following along with the dynamics and the kinematics of angular motion. Making use of torque equals I times alpha, omega equals omega naught plus alpha t. So I hope that's useful for you. And if you want some more example problems with physics and a few in astronomy, but mainly physics, physics.gpclements.com. Go to that website. You'll see a list of the available YouTube videos with how much time each video takes up and a description of what's there. This is totally free. There's nothing to register for or nothing to buy. You don't have to give your email address. There's no way to do that on the website. If you do like the YouTube videos, appreciate if you would subscribe to my channel, and you'll get an update when I post a new video.